Thank you very much, Taya, for joining us today. Over to you.
Thank you for having me. Appreciate the team for putting this together, as I think this is a pretty important subject as we enter uh, the advancement age of AI. Um, Ola did a fantastic job describing a lot of the microchip um, development process. What I'm going to do is probably share a little bit more about one particular application that I'm interested in, and this is built around mission critical uh, systems that are used for um, whether day to day automotive applications or um, defense and aerospace applications as well. So you guys can see my slides. So just to share, Lola Vision Systems, we're a fabless semiconductor company. So we're not doing a lot of the fabrication as Lola had mentioned earlier. We're more so on the design side. When it comes to chips that are utilized in these type of various electronics, one thing is good to understand is the challenges that these engineers face as they're trying to build these systems from the root, which is the different chipsets, all the way through the full physical system. So number one, they currently burn too much power. Power consumption is a very, very key attribute that engineers must look after because it obviously relates to the battery capability or capacity. And then there's the need for those chips to become faster and more accurate in terms of its performance. So if you're thinking about something that's computer vision related and you're looking through cameras on your system and you want to be able to tell what's in an image uh, in a quick manner, you need AI computation within these chipsets to actually be able to pull those things off and do it well. And then for the engineers that are working on software, they need to be able to tweak certain things that they may care about deeply within the system. And there's a lot of chip companies and chipsets out there that may not give you this advantage or opportunity to do so. They may sometimes kind of give you a chip and they say, you this is what you get. You use it however we design it for you, and that sometimes might be limiting for people that are designing around this. And then the idea around safety and security. This is a concept that we have to really make sure as a community that we at least are aware of, so that we can ask the right questions to make sure that these systems are being designed in a safe manner that is in your best interest as the user, right? Whether you're a passenger in the vehicle or you're a pilot controlling an airplane. Um, and then fifth, when it comes to custom hardware, these things are very, very expensive, especially for things that we consider to be mission critical. It could take up to 3 years and hundreds of millions of dollars to do. But even some of the smallest, easiest things that you think might be fairly easy to do could still be up to 20, $30 million to develop. And so what we're trying to do at Lola Vision Systems is address this. Um, to really go into AI compute, I wanted to bring an example that I think is kind of prevalent out there on the news. Folks understand NVIDIA to be one of the biggest market cap companies in the world. But how they got their start was with GPU technology, right? And this GPU technology was used for gaming applications initially and laptops to like actually render the images in real time to be a lot more crisp, right? And then they realized that they could um, use this technology in the data center for AI training. And it wasn't originally meant for that, but it kind of came up as an opportunity. And since then, the company is skyrocketed from like just a couple $100 million company to billions and billions of dollars per quarter per month or per quarter. And so one of the things that we want to do is share with you um, a different technology called a neural processing unit. And so this is something that's more tailored because from inception, it was made in mind to handle neural networks, which is effectively how some of these AI models are deployed after they're trained in the data center. And so for these devices that are on the edge, that are whether they're vehicles, drones, cars, spacecrafts, they have a finite amount of battery supply. And so if you really care about that power consumption, you want to make something that's more efficiently made specifically for that. And that's where this neural processing unit comes into play. So this is where Ola had mentioned a bit about how we want these chips to sometimes act or mimic the brain. And so you essentially get that with what they call an NPU. So apart from or different than a GPU, where these these processing elements in each of these arrays, they're all turned on in a GPU at the same time to try and do some calculations. But for a neural processing unit, it's scalable. So you only use the elements that you need in the moment of time when you're trying to run a specific algorithm or some type of AI computation. And what happens with that is you get less energy being consumed because you're not wasting the time needed for all of these elements to be turned on when you might not actually be needing to use them, which is very key. As far as key performance indicators, I want to educate the community about these because I think when you want to start talking the language about hardware and AI computation, you want to probably know some of these terms. And for one, let's start with power consumption. The unit for that is watts, and then for the performance, we have tera operations per second, or some people use trillion operations per second. There's floating point operations per second, which is just a different unit of data type that is being considered when running these AI computation. And then, a derivative of that is inferences per second, or most people know frames per second, which are camera phone, and how quickly it can capture images in a small amount of time. So all of these kind of fall in line as something somewhat similar when we talk about performance. But what's most important that we need to be taking a look at is the tops per watt. So you're basically taking the performance, dividing it by the power consumption to get the performance efficiency. And some other folks may use dividing that by the square millimeter per squared, which is just the area of the actual chip, or you can do it by cost. Either way, these are things that are being much more scrutinized in our community, in the engineering community. When developing a chip, most of the time, to demonstrate that your chip can actually achieve certain metrics, you want to start with an MVP, minimum viable product. And in a chip sense, this is something that you want to simulate in terms of that NPU and their performance within what they call an FPGA prototype. FPGA is a field programmable gate array. And not to confuse everybody, there's an ASIC that you obviously are going to create at the end of this chip design process. But then there's other types of chips that allow you to do this kind of prototyping, and that's what this FPGA is there for. The premise of the demo should be to run a head-to-head comparison against what you expect your chipset performance to be, right? So let's just say we take an arbitrary number of 2 tops running some open source AI model out there. And then, so you want to measure it within this FPGA that's emulating how this AI performance will run in the real world prior to you even having the physical chip made yet. And then from that, you can also model the power consumption and simulation. And that will allow you to be able to give some better confidence in your ability to meet a certain performance efficiency number. And this is the process to do so. For us, one of our flagship chipsets is the Project Ogun. For some folks that may or may not know, Ogun's in Nigeria, Ogun State. Uh, Actually, my dad's family is from that area, so I just decided to use that. But for some people, they might hear about it from deities, and it's the god of war and defense. And so my thought is, let's create this AI chipset that can be a staple for how we build AI chips, uh, whether it's on the continent or here. But regardless, we want to be able to make it a strong competitor in the field. And the thing that we want to be able to do is allow this chipset to be swappable. So that's where you get chiplets, and the hardware configuration changes can happen much faster when you're using chiplets, as opposed to when you're creating a new SoC every time you want to make a quick change. So these type of processors will run AI neural networks, like we mentioned before. There's different types of AI networks out there. I implore folks that are really interested in this space to learn the history of how convolutional neural networks are utilized. Now, more recently, folks are focused on transformer networks, and this is where you can get some of the chat GPT-like generative features. So that's what we want to be able to do at the edge in an environment where we might not have access to the cloud or to a communication protocol that will, give us a signal from somewhere. We might need to do all of that computation right there on the chip and telling a car what to do in the moment that it sees something or recognizes something. So all of those object detection, object recognition, or even the object tracking, all of that is done right here within this type of chipset. And then the data types is something that, it's important, but, for all intents and purposes, we may not get into it. We don't have the time to get into it right here, right now. But, the future of what I see is, for Africa to be able to manufacture a lot of their own products, we still need to make sure we're enabling the technologies underneath these products so that we can kind of go up the supply chain. And so, as we're looking at self-driving cars or defense systems to protect what's very valuable within the soil of the continent, we have to be able to create new technologies, new products, and chipsets is the best way to build your own custom products to achieve that. And so, for me, myself, I've been in the chipset space for 13 plus years. I went to Purdue University for my undergraduate degree in electrical engineering. From there, I went, and sold chips for major companies like On Semiconductor and Microchip Technologies. I loved what I did. I was very involved with just understanding the customer's challenges and pain points and supplying them the chips that make sense for them and their build. And then I left that. And I pivoted after I got my MBA from Arizona State to selling IP. So things like that neural processing unit or other processors that are used for running operating systems within your laptop or your cell phone, like these kinds of IPs, which are the core components within those chipsets, is something I became a specialist in. So I would sell these chipsets to companies like Samsung, Intel, Amazon when they wanted to do their own custom chipsets. And that allowed for me to really understand the ecosystem and the environment from the fabrication process to the actual decisions that were being made from executives on what kinds of IP components that they would utilize within their devices. And for me, I decided to create this company, Lola Vision Systems, because I wanted to create a device that I could trust, that I know is going to have the proper safety and security built in, so much that I would feel comfortable at someday being able to have Lola, my firstborn daughter, actually be in these vehicles. And so that's the motivation behind the company, and that's my tribute to my kids and my future. So thank you, everybody. Feel free to ask any questions. I try to return a little bit of time for the team. Thank you.